Before we start the show, don't forget to check our new ebook, Kill All Bugs, Learn Software Testing in One Day. For a limited time, it's only $9.99. Links in description.
Welcome back to the Deep Dive. Today we are strapping on our hard hats and going deep. We're getting into the most fundamental layer of computing, the invisible architecture that lets every device you own actually, work. We're drilling down into the essential and often kind of confusing distinction between system software and application software.
It sounds technical, but it really isn't.
No, it's not. And the sources you sent over were great, very structured. But a bulleted list doesn't really give you insight, does it?
Not at all.
So our mission today is to give you that clear map. We want you to understand the why. Why? One is for survival, and the other is for, well, getting things done. It's like the manager versus the worker.
And that distinction is crucial for everyone. I mean, not just for developers. Understanding this split is the key to understanding how any device works. Or, more importantly, why it fails.
Right.
If you know whether the problem is the foundation or just the tool you're using, you get a much better handle on what your tech can and can't do.
Okay, let's unpack this then. We have to start with the foundation, the master controller, system software. Let's just call it SS.
The deep layer.
The sources define it as the set of programs designed to control and manage the operations of the computer hardware. That sounds a little dry. What does that actually look like?
It looks like total command. Think of system software as the operating environment. Its whole job is resource management. It's the ultimate traffic cop for the entire machine.
The traffic cop?
Yeah, it handles memory, decides which program gets to use the processor, manages your keyboard and mouse, and enforces security.
So without it, you've just got a box of parts.
A very expensive paperweight,
Yeah.
exactly. The goal of SS is just to make the whole operation faster, more effective, and, most critically, secure. It makes sure no single program can just take over and crash everything.
Okay, so if SS is the essential low-level manager, the operating system and its tools, then application software, or AS, must be the layer we actually interact with.
That's it. AS is what most of us just call software.
The apps on my phone.
The apps on your phone, the programs on your computer, it's built for a specific task. If you're editing a photo or typing a document, you're using application software.
I like how the source material calls it a mediator. It's the go-between, right?
Precisely. The application can't talk directly to the hardware. When your word processor wants to save a file, it can't just reach in and grab some space on the hard drive.
It has to ask permission.
It sends a request to the system software, to the OS, which then manages everything. The application is just there to meet your specific need, and it's built completely on top of that SS foundation.
This dependency thing.
Yeah.
This brings us to what I think is the most fascinating difference. Their DNA. The language they speak.
Yeah, this is the deepest split. System software has to talk directly to the processor, to the memory controller, so it has to be written in a low-level language.
We're talking machine code, assembly language.
Exactly. It's incredibly close to the hardware. We say it's close to the metal.
And what does that mean in practice?
It means it's incredibly fast and efficient. But, and this is a huge but, it's brutally difficult to design and to debug. Every single command has to be perfect because you're dealing with the machine's raw logic.
Which is why building a stable operating system is such a massive undertaking.
It takes huge teams, decades of work, and that's the cost of efficiency. But if you built every application that way...
Nobody could ever build anything quickly.
Right. That's why application software uses a high-level language. Python, Java, C++, Deplechet, things that are built with human logic in mind, they're much, much easier for developers to work with.
And that lets people innovate, design new things fast.
It does. And if you look at their life cycles, when they're running, it all connects back to the language.
How so?
Well, system software is the infrastructure, so it can run independently. It starts the moment you power on your machine, and it runs continuously until you power it off.
It has to be there.
Otherwise, the computer is just off. But application software is totally reliant. It cannot run on its own. It needs the OS to create that stable environment.
So its life is tied to me, the user.
Completely. It starts when you click the icon and it stops the moment you close it. That timing difference really shows their purpose. SS is general purpose. It manages the system for everything.
And AS is specific purpose. It only exists to do one thing, like send an email or play a game.
Exactly.
Okay, let's connect this to the user experience. You mentioned security. How does this separation actually make the whole system more stable?
It's a deliberate design choice. You, the user, almost never interact directly with system software. It's all happening in the background.
Okay.
So think about what happens when your browser and application crashes. Maybe it has a memory leak or some other bug.
It just closes. The app dies.
Right. And most of the time, that's all that happens. That's the system software doing its job. The OS sees this one application misbehaving, trying to use too much memory, and it isolates it.
It shuts it down.
It shuts it down before it can take the whole system down with it. That separation ensures that a bad word processor doesn't destroy the machine's ability to even operate.
That makes the whole installation process make a lot more sense, too. The crucial layer goes on first.
Of course. System software, especially the OS, is installed right at the beginning. It's prepackaged to manage that specific hardware.
But the application software.
That's installed purely based on what you need. You decide you want a photo editor, you install it. Its classification is all about utility, how it shares resources.
Which brings us to this idea of cruciality. SS is obviously non-negotiable, but the source says AS is not extremely important for the system's functioning. That feels a bit strong.
I see what you mean. It is technically true, but only from the perspective of the machine's survival.
Okay.
If you delete every single app from your computer, the operating system will still boot up. It will still run perfectly. It just won't be able to do anything useful for you.
So application software isn't crucial for the machine's operation, but it's absolutely crucial for the user's operation.
That's the perfect way to put it.
Let's give everyone some really tangible examples, especially for the system software side, because it's more than just the operating system, isn't it?
It is, yeah.
So we all know about operating systems. They're number one. But the second type, programming language translators. That's one people might not think about.
But they are absolutely vital. This goes right back to our language discussion. These translators, compilers, interpreters, they're like the diplomatic core of the system.
How so?
They take the instructions written in that easy, high-level language by a developer.
For an application.
For an application, yes. And they translate it into the raw machine code that the low-level system software can actually understand and execute. Without them, you couldn't run any of your apps. They bridge that huge language gap.
The third one is communication software. This is basically the internet, right?
Mm-hmm.
Network drivers, all the plumbing that lets your device connect to anything.
All the invisible plumbing, yes.
Yeah.
And finally, you have utility programs. These are sort of a hybrid.
Like a disk defragmenter or a backup tool.
Exactly. You, the user, might start them, but they operate at a deep system level. They're doing maintenance to keep the core system software running clean and fast.
Okay, so then quickly, for application software, these are the things we all know and use every day.
Right. You've got your big productivity tools, word processing, spreadsheet software for numbers, database software for storing data.
The office stuff.
Pretty much. Then you have the creative and leisure tools, graphics software for art and photos, education software, and of course, entertainment software for games and movies. They all do one specialized thing.
What's really interesting is how these different jobs are reflected in the software's actual design. The size, the speed, all of it comes from their role.
It's a direct reflection. If you look at system software, it's designed for one thing, speed. It's physically closer to the hardware.
And it's written in that low-level language.
Which makes it inherently smaller in size, it needs less storage space, and it's incredibly fast.
But the trade-off is massive. It's so hard to design, hard to understand, hard to manipulate. You don't really interact with it.
Then you contrast that with application software. It needs a graphical user interface. It needs all these features for the user, so it's naturally much, much bigger in size. It needs more storage.
And it's easier to design.
Way easier, thanks to those high-level languages. And it's meant to be interactive. It sacrifices that raw, low-level speed for accessibility and rich features. It's designed to be replaceable. System software is designed to be permanent and stable.
So if we pull all this together, the core insight is that computing is built on this paradox. You need this complicated, fast, secure, low-level foundation.
The system software.
So that you can then enable the creation of easy-to-use, flexible, high-level tools.
The application software. It's the ultimate hierarchy. The visible, user-friendly layer is completely at the mercy of the hidden, low-level system running underneath. If the manager is slow, the worker can't do their job well.
So what does this all mean for us? The next time we install a huge 10-gigabyte game or download a tiny little OS security update.
Well, think about trust and security. That system software, the OS, is the gatekeeper. It's written in that complex code that's so hard to check for bugs. That's your biggest potential vulnerability.
Right.
Companies could, in theory, write everything in easier, safer, high-level languages, but they don't. They choose the brutally difficult path for the OS. And why?
For performance.
For extreme performance and direct hardware control that you can only get from low-level code. They risk all that complexity just to make sure the foundation is the absolute fastest, most efficient base possible for every single application that runs on top of it. That one engineering choice is what keeps our entire digital world running.
A lot to think about the next time you see a 40-gigabyte application getting installed. Thanks for joining us on this deep dive into the architecture of computing.
Hey, yo, haven't you checked out our new book yet? Link in description.